Hello, everybody, and welcome to my talk at ISCA 2020, where I discuss our work on focused value prediction. The CPU, as we know today, has come a long way from the earliest scalar processors to today's highly out of order, deeply pipelined superscalar processors. The evolution of the CPU can be shown with the performance versus effort curve, as shown in the figure below. Each successive CPU spends more and more effort to extract parallelism out of the workloads and therefore increase the performance. However, we are now flattening this curve and we are beginning to approach the ILP wall, a situation where there is not enough parallelism left in the workload to increase the performance. Value prediction was proposed as a means to break true data dependencies and thereby increase the ILP of the program and scale through the ILP wall. So how does value prediction work? Consider the example program shown below, which has 8 instructions in a dependence chain and executing serially. The ILP of such a program is equal to 1. If we were to value predict a few of the instructions as shown below, we would obtain 4 instruction chains which are independent of each other and can execute in parallel. The ILP of the program has now become equal to 4. Thus, by breaking true data dependencies, value prediction enhances the ILP of the program. Many value predictors have been proposed till date. The earliest value predictors like last value and stride predictors were IP-based predictors, whereas more sophisticated designs like Eves and composite predictor use program context as well as smart allocation schemes to predict more and more instructions. The fundamental philosophy behind each of these predictors is to predict more instructions and therefore increase the performance. However, this philosophy does not take into account the power and energy costs of value predictions. There are a few power-intensive operations in value predictions. First is the value table. The value table stores all information required for value prediction, such as PCs, predicted values, confidence counters, etc., and is generally implemented using SRAM arrays in the core of the CPU. The bigger this table, the more static power and read and write energy it consumes. The next power-intensive operation is to provide the predicted value to the dependents. Typically, the predicted value is copied from the value table into the register file from where it can be sourced by the dependent instructions. As we predict more and more instructions, the number of register while write operations go up, and this increases the power consumption of the register file. The third power-intensive operation is to validate the value prediction. To do this, the predicted value is read out from the register file and compared against the actual value obtained through execution. As more and more instructions are predicted, the number of register file read operations go up, and this also increases its power consumption. These scenarios show us that predicting more instructions is actually harmful for power and energy, and a solution is required which can provide more targeted coverage and achieve performance efficiently. With this in mind, the outline of my talk is as follows. We will first understand the notion of the critical path of execution and how it interplays with value prediction. We will next understand the various kinds of data dependencies and how the choice of right data dependence matters for performance and power. We will then detail our proposal focus value prediction in detail and also discuss its results. And I will conclude my talk with a summary of our work. Let us understand the concept of critical path. We use the following program shown in the table below. It has 9 instructions, and the columns A, D, and WB denote the allocation, dispatch, and write back times of the corresponding instructions. As we can see, the total execution time of this program is equal to 241 cycles. Another way to represent this program is by means of dependence chains, as shown here. Instructions 5, 6, and 7 comprise the first dependence chain, and the rest of the instructions comprise the second dependence chain. The critical path is the path having the longest wait of execution, and as highlighted below, the critical path runs from instruction 1 to instruction 9. Its total length is equal to 241 cycles, which is the execution time of the program. Another thing to note is that instruction 8 is an LLC miss and takes 200 cycles to execute. Such an instruction will surely stall retirement of instructions in the out of order, and we denote such retirement stalling instructions as the root of the critical path. We will further elaborate this concept next. We now understand how value prediction can be used to shorten the critical path. In the first scenario, if we try to predict instruction 8, which is the LLC miss, we see that we achieve an savings of 1 cycle, and the critical path has shortened to 240 cycles. This is a small saving, and this is because value prediction does not save the latency of the predicted instruction, it rather removes its dependence from the critical path. Therefore, predicting a long latency instruction will not achieve higher performance. Therefore, if you predict another instruction, suppose instruction 1, we see that the critical path has shortened substantially more to 212 cycles. If we explore further and predict instruction 4, we say that the critical path is shortened even more to 205 cycles. The best case for value prediction would be to predict all instructions, and in this case, the critical path becomes equal to 204 cycles. As these scenarios clearly show us that some instructions matter more for performance than other instructions, and this is also true for instructions that lie on the critical path, and therefore, the focus of value prediction should be to predict instructions as close to the critical path route as possible, as is highlighted by the third scenario. Having chosen the right instruction to predict, we now answer the second question, which is the right dependence to predict. Consider the example shown below. The instruction in red is the root of the critical path and needs to be accelerated. Naturally, the first choice of instruction to predict would be instruction L. However, we suppose that instruction L is not predictable. Therefore, the second best choice of instructions to predict will be the instructions behind it. We see that instruction L has a register dependence with A and B and a memory dependence with S. If we were to predict A and B, we would break the register dependence and the load address will be available immediately. However, the load will still have to wait for the store data and therefore cannot complete. However, if we were to predict the store S and break the memory dependence, the load data will be available immediately using the store. Further, we will also not require the load address for carrying out a prediction. This example shows us that predicting one memory dependence is actually better for performance than predicting two register dependencies, and thus forms the second guiding principle of focus value prediction. We have now seen the two guiding principles of focus value prediction, and we now discuss our method of focus training. The goal of focus training is to identify the smallest set of value predictable instructions that are closest to the root of the critical path, and we do this through a series of steps. The first step is to identify a retirement stalling instruction, which we also call as the root of the critical path. We add this instruction to the value predictor. We also add its parent sources to the value predictor. Parent sources are instructions which produce the sources of the retirement stalling instruction. The value predictor then trains for all these instructions, and if any instruction is found to be highly predictable, we do a value prediction for it. If, however, some instruction is found to be not predictable, then we go back and add its parent sources to the predictor, and the value predictor now trains for the new instructions. This cycle repeats until all instructions in the value predictor are highly predictable, and at this point, focus training has completed and we can begin to predict all instructions. Now we elaborate all the steps of focus training in more detail. The first step is to identify the root of the critical path, and to do that, we use the reorder buffer. Consider the snapshot of the reorder buffer shown below. The slots in blue show instructions which have completed execution. The slots in red show instructions which are under execution, and the slots in yellow have not yet begun execution. We snoop all instructions which are undergoing execution, and for each of the instruction which is executing, we check whether its distance from the retirement pointer is less than the commit width of the processor. For instance, in the figure, instruction M is executing and its distance from the retirement pointer is less than the commit width of the processor. Such an instruction will stall retirement and therefore is critical for performance and is added to the critical instruction table. We also mentioned that branch misprediction may be critical, but we do not add them to the CIT for reasons that we elaborate in the paper. We have now identified the root of the critical path, and we go further to identify the rest of the instructions to predict. We use the following example for our reference, where instruction M is the root of the critical path. Hence, it has been added to the value table. We have also added its parent source K to the value table, and we now begin focus training from this point. The prioritized training for instructions K and M, and if suppose instruction K is found to be not predictable, then we use the RAT to find its parent sources, which are J and L, and we add them to the value table. Subsequently, K is also invalidated, and the predictor trains for the new instruction. If we now find that instruction L is not predictable, then we again use the RAT to find its parent source C and add it to the value table. If we go ahead and also find that instruction J is not predictable, then we have to add its parent sources. However, we now see that J has a memory dependence with S and a register dependence with A and B. And therefore, as we have seen before, the memory dependence gets priority over registers. Hence, we add S to a separate store load PC table in the value predictor, and this achieves priority over A and B. In the course of training, we now find that instructions S, C, and M are highly predictable, and this marks the completion of focus training because all instructions in the value table are highly predictable, and no further instructions need to be found to increase the performance. This completes focus training. Now that we have identified what are the best instructions to predict, we now elaborate what are the value prediction techniques that we apply for the chosen instructions. We use three techniques, namely last value, context value, and memory dependence prediction as described by Tyson et al. Last value prediction checks if a certain PC produces the same value again and again. Context value checks if a certain PC and branch combination produces the same value again and again. And memory dependence prediction checks if a given store and load have a high correlation of addresses, and therefore the store data can be used to predict the load data. The first two predictors, LV and CV, are trained using the execution unit, and the information is stored in the value table. Note that we use a unified value table for LV and CV, and the distinction between them is made through the indexing function. The MDP is trained using load store queue because it records information concerning the addresses as well as load store forwarding. And this information is stored in a separate store load PC table in the value predictor. When a new instruction comes in, it is first predicted using LV, followed by MDP, followed by CV. And if it is not predicted by any of the three techniques, then we move to its parent sources. This priority ensures that we use the best and most efficient prediction technique for a given instruction before moving to its parent sources. We have now seen what are the various components of focus value prediction, and I will now show a comprehensive picture of how focus value prediction is implemented in a typical processor pipeline. The first component is the CIT. It is implemented in the front end and it trains from the execution unit. It records instructions which are going to stall retirement and achieves confidence on them. After decode, every instruction queries the CIT, and if an instruction has high confidence in the CIT, it is marked critical. Next, the critical instruction can use the RAT to find its parent sources, and subsequently the critical instruction as well as its parent sources are added to the value table through the execution unit. The execution unit also trains the value table further. After decode, each instruction checks the value table, and if it has a high confidence, its value is predicted. Next, the LSQ trains the memory dependence predictor using load store pairs. Whenever a store forwards data to a load, this information is recorded in a store load PC table in the front end of the program. If a load has a high confidence with the store load PC table, we do a memory dependence prediction for it in the out of order. This picture provides a complete implementation of FPP in a processor pipeline. We use the following. We have now seen how FPP works, and we now show our results of our experiments on the following core configurations. We use two core configurations for our evaluation. The first is called Skylake, and the second is Skylake 2x, which has double the out of order and execution resources as Skylake. We have 60 diverse single-threaded benchmarks for our evaluation, which includes Spec 06, Spec 17, as well as some server benchmarks. The following graph shows the performance of FPP over a Skylake baseline. Overall, FPP gets 3.3% geomean performance over a Skylake baseline while predicting 25% of the loads. On a Skylake 2x baseline, it predicts 24% of the loads but achieves a much higher performance of 8.6%. To understand the performance increase, we see the following S-curve. The S-curve shows that the red line shows the performance of FPP over Skylake, and the blue line shows the performance of FPP over Skylake 2x. As we can see, many benchmarks have a more performance on Skylake 2x. And the reason for this is that Skylake 2x has a bigger instruction window, and therefore this can be used to extract the increased ILP generated by value prediction. On the other hand, Skylake has a very small instruction window, and this cannot extract the increased ILP that has been generated by value prediction. Hence, the gains on Skylake 2x will be higher. We also compare FPP with other state-of-the-art predictors in literature, namely the MR by Tyson et al. And the composite predictor from Shake. As we can see, FPP achieves near comparable performance to the state-of-the-art predictors at just 1/8 the storage. More importantly, at the same storage at 1 kilobyte, FEP assumes almost twice the performance of the state-of-the-art composite predictor. This clearly highlights the efficacy of our focus training mechanisms. To further emphasize the quality of our focus training, we perform the following 4 experiments. The first experiment, we only predict L1 cache misses. In the second experiment, we predict instructions which lie on the backslice of cache misses. The third experiment is our proposal focus value prediction. And the fourth experiment, we use a best possible oracle criticality, where we use a data dependence graph generated in hardware to detect critical paths and predict loads that lie on the critical path. The following graph shows the results of these experiments. In the first experiment, gives no performance. As is expected, predicting an L1 miss will not give us a lot of performance because value prediction does not save the latency. And therefore, this experiment does not give us meaningful performance. In the second experiment, gives us more performance of 2.1% when we predict instructions that lie on the backslice of cache miss. However, this falls short of the performance of focus value prediction because L1 cache miss does not capture all critical paths. It does not capture dependence chains which are longer than the out of order critical window. FVP, on the other hand, captures both long dependence chains as well as cache misses and therefore has superior criticality detection, and hence its performance is higher. The Oracle criticality has higher performance than FPP as well as a lower coverage. However, it uses a graph creation and detection mechanism which is impractical to implement. Nevertheless, this example shows us that our simple criticality and focus training mechanisms can achieve performance as close as possible to an ideal criticality detection. To summarize the power benefits of FPP, FPP requires just 1.2 kilobyte of storage and hence the structures are very small. This reduces the static power consumption as well as the read and write energy. Also, FPP predicts much less instructions than other predictors and hence the number of register file read and write operations are less. This also contributes to a reduction in the register file power. To summarize our work, conventional wisdom is to increase value prediction coverage. However, this philosophy does not take into account the power and energy costs of value prediction. To this end, we propose focus value prediction, whose goal is to identify the smallest set of value predictable instructions that lie close to the root of the critical path. We demonstrate a superior yet low-cost criticality detection mechanism compared to previous works. We also show an iterative method to target the most optimum set of instructions and data dependencies that can achieve highest performance at the minimum cost. And this gives FPP a performance near comparable to the state-of-the-art processors at just 1/8 the storage. And therefore, we believe that FPP is a viable mechanism which can be implemented in modern out-of-order processors and thus help them scale the ILP wall. Thank you.